Okay, I want to take a few minutes to talk to you about a concept called work done by friction, which a synonym of that is heat, also called thermal energy. So if you hear me or somebody else talking about work done by friction, or hear about heat, or hear about thermal energy, they really mean the same things in a mechanical energy context. Let me tell you what I mean by that. Let's say we got a situation where there's a 2 kilogram mass sitting on top of a 3-meter high incline, and let's go ahead and say that by the time this thing slides to the bottom, I should probably mention that this thing starts at rest. By the time it slides to the bottom, it acquires a speed of 4.5 meters per second. Let's take a closer look at some of these numbers here. For instance, its initial potential energy, I'll write it out like this, U naught. Well, its initial potential energy is going to be 2 times 9.8 times 3. So we can go ahead and calculate that, and we get 58.8 joules. Well, let's take a look at the kinetic energy at the bottom, because we know that since we're going to set our 0 point now at the bottom, most likely it's not going to have any potential energy at the end, but it will have some kinetic energy. So let me go ahead and calculate the final kinetic energy. It's going to look like this: 1/2 mv squared, 1/2 times 2 times the velocity at the end, which is 4.5 squared, and you get 20.25 joules. So it's kind of interesting as you consider this. It had 58.8 joules of energy at the beginning, of mechanical energy. It had no kinetic because the velocity was 0 right there. But the total mechanical energy is 58.8 joules. It slides down to the bottom. It loses all of its potential energy, turns into kinetic energy, but I only have 20.25 joules to speak of. There's some missing energy here. And specifically, there's a change in energy of, let's see, my final, which is 20.25 minus my initial, 58.8, negative 38.55 joules. We lost a bunch of energy. Where did it go? I mean, I thought we were told that energy can't be created or destroyed. It can only change from one form to another. Well, that's exactly what happened. In problems previously, when we did conservation of energy problems, we went from potential to kinetic. Now there's another form of energy involved. Let's go ahead and take a look at that conservation of energy equation that we've been using. K naught plus U naught equals K plus U. So in this case, there was no initial kinetic energy and no final potential energy. So if you plug in your mgh naught right here for U naught, and your 1/2 mv squared right there, and you were to cross out the m's, and then if you were to do 9.8 times the height of 3 equals 1/2 v squared, you're going to find out that v should have been about 7.67 meters per second, but instead we're only getting 4.5 meters per second. So there's less speed here, and as we already showed, that there's some missing energy. Well, the key here is that missing energy showed up as heat. It showed up as thermal energy. It's another way to say it, the work done by friction was negative 38.55 joules. And we're going to have to account for that in our conservation of energy equation. We can no longer say K naught plus U naught equals K plus U. That was only for cases where there was no friction. What are we going to write now? We'll check it out. We're going to write this: K naught plus U naught equals K plus U plus heat. And we can just as easily call that last one heat. We can call it thermal energy, or we could call it work done by friction. But whatever the case may be, this is what you would use now. And this heat is always going to be a positive number that we're going to plug in, because heat's going to show up as some positive heat output. So now if you use this equation and you consider what we had going on before, well, we had no initial kinetic energy, we had no final potential energy, we did have some initial potential, we did have some final kinetic, but we also had some heat produced because there was some friction. And now you can see it makes sense that this is going to be less than this because there's also some heat involved too. So let's assume the problem in the problem you were asked to calculate the amount of heat generated. Well, what I would do is I would go ahead and plug in the mass of the block, 9.8, the height of the incline, 1/2 times the mass of the block times the velocity of the block at the bottom, which you can see was 4.5. And we have to square that, and you add that to the heat. And at this point, to solve this equation, all you do is take this term and move it over to the other side and make it negative, and then you'll get heat. And you're going to get heat equals 38.55 joules, which is what we got earlier. And so that's just one way to find the heat, the amount of heat that's produced. Now, can we quantify or equationify this thing called heat? Sure. I would call it the work done by friction. If you think about what work is force times distance times cosine theta. So for force, I'll plug in the friction, if I'm trying to find the work done by friction, times the distance times the cosine of the angle. Now, friction almost always opposes motion. So if something's moving to the right, friction is to the left, and that would be a 180-degree angle. Of course, the cosine of 180 is -1. And so really what we have here is that the work done by friction is negative whatever the force of friction is times the distance. And that's going to be negative mu times n, because friction is mu times n, times the distance. And so the work done by friction is this. And it is true that the work done by friction is always a negative number. However, when we talk about that in terms of heat, we just leave the negative off and we say there's a positive number of joules of heat produced. So what I would do if I were you is I would just kind of keep in your mind work done by friction technically is a negative number, but for all practical purposes it's just going to be easiest to say this, mu times n times d. You know, absolute value, or you can just leave those off. And just remember work done by friction is mu n d. And even though it is truly negative, if you want to be technical about it, you can go like that, but then you can write this out. Heat equals mu n d. And that's just a good thing to know. The heat produced is equal to the work done by friction. Now, in some problems, they're going to give you the coefficient of friction, and you're going to be able to calculate the normal force, which is sometimes equal to mg, sometimes it's not mg. It depends on what kind of funny stuff is going on. For instance, if it's on an incline, the normal force wouldn't be mg, it'd be mg cosine theta, right? Or if you push down on a box or lift up on it a little bit, the normal force will be altered. But anyways, mu times n times d is the heat. And if they give you mu, you can go ahead and calculate heat that way. If they don't give you mu, you're going to have to go ahead and try and calculate heat this way by plugging in the conservation of energy equation. Now, let's talk again about this equation really quick in terms of mu n d. We could rewrite this equation like this. K naught plus U naught equals K plus U, and that's all there is to write. If there is no work done by friction, or if there's no heat. But if there is friction and some heat produced, you're going to have to write either heat over here, or when you read the problem, they're giving you a coefficient of friction in the problem. It's probably to your best interest just to go ahead and write out mu n d right now. And you'll be plugging in your coefficient of friction there. Maybe they'll be asking you to solve for a coefficient of friction. But this is what the equation looks like now. That's the conservation of energy equation for when you have mechanical energy but also heat. Let me give you an example of how this problem works. Let's go back to the hockey puck problem that we had a while ago. And the hockey puck problem, this was something we're studying in the force unit. Let's say I've got the weight pulling it down. I've got a normal force pushing up on it. It's sliding to the right, but that means the kinetic friction is to the left. So this hockey puck is slowing down as it slides to the right. And those are the forces on it. Remember, to find out how far this thing is going to go, we had to do a bunch of stuff. What we had to do was we had to, think about it in terms of, well, A is going to be net force over mass, and the net force on this thing was the friction, to the left, but friction was mu times n, but the normal force was equal to mg, and then the m's canceled, and so what you had was acceleration equals negative mu g. And that's kind of a long way of getting there, but that's an important result, because then what you do is you plug it into this equation right here, You take that and you plug it in for acceleration. And then, if this thing is coming to rest, you would say the final velocity is 0. You plug in the initial velocity. You plug in this negative mu g there for a. And then you can solve for distance, the distance it takes to slow down and come to rest, that hockey puck. But is there a way to do this not using Newton's laws and not using kinematic equations? Sure, you can use the conservation of energy equation. Let's see how that works, and let's see how easy this problem becomes. So we'll start by asking ourselves some questions. Does it have any initial kinetic energy? Yes, it does. So we would just write out 1/2 mv0 squared. Does it have any initial potential energy? Nah, it's kind of just on the ice. And we'll make the 0 mark the surface of the ice. Does it have any final kinetic energy? No, it's going to come to rest. We want to find out how far it goes before coming to rest. Does it have any final potential energy? No, it's still just on the ice. Well, was there any heat produced? Sure there was. There's a bunch of friction acting on that puck, so we would write this out now. Mu times N times D. And so we just use the conservation of energy equation, talked ourselves through it to set up 1/2 mv0 squared equals mu ND. We can simplify that a little bit in this way by getting rid of the normal force and substituting in mass times gravity for the normal force, because you can see these things are equal. And then we can't forget to multiply it by d. What's cool right here is the m's cancel out, so you're left with 1/2 v0 squared equals mu times g times d. And you can pretty easily figure out how far it's going to go before coming to rest right now. You just have to plug in mu, you plug in 9.8, you plug in the initial velocity, and don't forget about the half and the squared. But yeah, you can solve for d, and that's pretty easy. A lot easier way than free body diagramming it, doing the Newton's second law expression, using the kinematic equation. It's a lot easier way. So that's kind of the power of using conservation of energy and work done by friction. Just one other little side problem. It's not really technically related to the work done by friction, other than just the idea there is heat produced in this situation I'm going to show you. Let's say I have two blobs of clay, for instance. This is a 5 kilogram blob of clay. This is a 2 kilogram blob of clay. And the 2 kilogram blob of clay is moving at a speed of maybe 3 meters per second. This 5 kilogram blob of clay is moving at a speed of, well, actually, I think I'm going to change this a little bit. Instead of 3 meters per second, let me erase that and just write 30 meters per second here. And this 5 kilogram blob of clay is moving at a speed of 12 meters per second. Okay? So anyways, when these two things hit each other, believe it or not, and we'll get into this when we study a concept called momentum, but they're going to hit each other and they're going to come to rest. And when they come to rest, there's going to be a tremendous loss of kinetic energy. I mean, if you think of it right now, the kinetic energy of this guy is 1/2 times m times 30 squared, right? Kinetic energy of this guy is 1/2 times m times 12 squared. If you actually put joules on these things, here's what you get. You get 900 joules of kinetic energy for the small guy, and there's 360 joules of kinetic energy for the big guy. He's traveling a lot slower, and speed is squared, so a lot less kinetic energy there. But the question becomes, if this guy had 900 joules of kinetic energy before the collision, and this guy had 360 joules of kinetic energy before the collision, that's a total kinetic energy of 1,260 joules, and all of a sudden, once they hit and crash together, they just come to rest. Where did all that kinetic energy go? And the answer is heat. It all turned to heat. Maybe a little bit of sound energy if it made a sound, but if they're clay and blobs, maybe they don't make much sound. It all turns to heat. So the question becomes, how much heat was produced? Easy, 1,260 joules approximately, which is equal to just the sum of the initial kinetic energies. So you'll see a problem like that in some of the work that you do. But this is heat energy as it relates to mechanical energy, and so good luck trying to apply it. The problems aren't that hard, but you just have to understand the concepts well and practice them. So that's it for now. Have a great day.